Hi friends, this is Rizal again with another short video. This will be real short. Yeah, it's a video on GPU accelerated image processing suite implemented in CUDA using the C++. Now the goal of this project is to take the traditional sequential image processing algorithms like blurring or edge detection, yeah, the Gaussian blurring, edge detection, yeah, and the sine wave, and then port them to NVIDIA's CUDA platform. Now, the architecture follows a strict pipeline. We load the PPN images into a floating point array. Then we allocate separate memory buffers on the GPU for red, green, and blue channels, and then execute parallel channels. Now, I'm going to move quickly through, and please bear with me. Yeah, we look at the code, but it is so long, so let me just go quickly over the implementation aspect. Um, so now the main function and the memory allocation logic. So this is where we have the main function coming in. So we use a unified command line interface, and the C++ code passes the operation argument, whether it's blur, right? Whether it's blur, it is edge, or it is a sign of the posterize. Okay, yes. And that dispatches the correct kernel. Now, crucially, the entire execution in the in this part, right? High resolution clocks. This allows us to measure not just the kernel time, but the entire round trip performance, including the overhead of the CUDA memory copy. But for memory management, um, which is not here, we are working with raw pointers. Yeah. So we allocate device name using a CUDA malloc, and then the transfer data using a CUDA memory copy host device. Then we treat the image channels as contiguous 1D arrays, even though the image is 2D, right? This simplifies point arithmetic in the kernel, which we look at next. Okay. So now, um, let me just skip the grid and let's look at the main four operations that were used. Okay. Now, with the Gaussian blur operation, it's smooth images using a 3x3 filter with Gaussian base widths. Okay. So, um, blah, blah, blah. Um, and again, this one will normalize the weights. We process the 3x3 neighborhood around correct pixels. Okay. And then accumulated weights, weighted sum from neighborhood. Then we blend between original and blend based on parameter string. And to make sure that it fits the frame, right? Don't forget that. This forces the index to stay within there. So here we have the neighbor, right? Right here. So this part is where we have to fit within the boundary checking right here, and then here we accumulate them to fit the neighborhood. Okay, still within the valid image range. Finally, we perform image interpolation. Okay, and the image has a soft, diffuse appearance with fine details with this to create a smooth effect as if it's viewed slightly out of focus. So this is the image right here, blurred, as the name suggests. Okay, now let's go to the edge detection. So with the edge detection, this is how we handle image boundaries. Here, so we handle image boundaries. And then here, we look at the two gradients, the subdual X operator for vertical edge detection, and then the subdual Y operator for horizontal edge detection. Then we calculate the edge magnitude from gradient components, and then we use the threshold to make sure that it's also it does not exceed the edge threshold. Okay, does not exceed the edge threshold. So it should be one. If it exceeds the edge threshold, or otherwise you write zero. Okay. So this image primarily shows the outlines and contours of objects from the original photo with sharp transitions in brightness um, highlighted, making the image look like a line drawing. Okay, so this is it right here. This is the produced image. Okay, and the sine wave. When the sine wave produces synthetic images with animated wave patterns using mathematical computation. Okay, and this is where we calculate the sine wave position. Then we oscillate around center. We normalize the vertical coordinates. We determine the frequency from the waveline. And then here, the, we create scalar gradient based on vertical position. So don't forget, it will be like a wave, right? So it will give us a synthetic abstract appearance. And this is it right here, synthetic abstract appearance. And then the final one, the posterization. Yeah, it reduces image fallacy, creates a stylized effect. Okay. So these colors in this image have been reduced to a limited number of distinct shades, resulting in flat color areas and a graphic, often artistic visual style. And here we can this is the whole code right here. Okay. And so concluding, this and don't forget that posterization has its picture right here, a stylized effect, right? Okay. So in conclusion, now again, the complexities are all here. These three are almost linear. This is linear, but on the expensive side, right? Because k times n, that is 5. Okay. Okay. Now, um, in conclusion, this project demonstrated that by managing memory explicitly and then utilizing 2D thread configuration, we can effectively process high resolution images in milliseconds. We can effectively process high resolutions in milliseconds. Yeah. So the code is modular, allowing for easy addition of new kernels and reborns to handle. All right. So let's go back to the terminal. Yeah, let's do this. And I'll share my screen real soon. Let's see what I do. See what we do. Okay. Okay. So this is my editor right here. And these are all the codes I used. And so I'll not waste the time. I'll just jump into the implementation. This is everything there is, and with all the explanations right there, here's how we convert the picture and we debug an error and handle all errors. This way, we manage in our functions. And then we have, yes, it's a lot, the CUDA kernel. So we have the Gaussian blur, edge detection, and sine wave, and then the posterization artistic. And yeah, it's a lot. All right. So let me just quickly and reload. Don't forget to load because there's an include that you have to load that. Okay, now let's implement and we have our images. So here it shows that we have been able to run successfully. Yes. And since I was not able to use the Send Center um, effectively, I did a serial on Python. Now I'll share my screen real soon with the Python. Okay. So with the Python, yeah, just like we saw in the other documents, where I use the serial progression right here, and this right here is the edge detection like we saw earlier, the Gaussian blur, the posterizing mode, and then finally the sine wave. So these are proofs of the run our generated pictures. So thank you, and I'll see you again in my next video. Stay tuned. Bye bye.